we can start. One second, let me check. Recording. Yes. Okay. So first, the session will be on current mill. We will have the numericals, the problems based on current mill. Before that, before we go there, we will study why we need circuits. That is the advantage of using current source. So we know when we bias device, we use different color. So these are the two types of sources which we can use in our circuits. So let's look at the advantage and disadvantage by using the mathematical expressions. We know if we have a MOSFET in saturation, current can be given by kW by 12 VGS minus VTH whole square. So this is for NMOS. Same goes with the PMOS. Okay. If we calculate GM, that is transconductance, I will get kW by L VGS minus VTH, right? Also, if I use again the same expression I can write GM as 2 kW by L IDS. I here it is I. Okay. So I have expression 1, expression 2. I have two expressions for transconductance. So now we will see the sensitivity of this parameter. This is an important parameter for a MOSFET. So it dictates your gain, linearity performance and other performances. So this is an important factor. We will see why we need current source instead of a voltage source. So from expression 1, we see that the expression depends on the expression threshold voltage, right? It depends on threshold voltage, but we know VTH, which is a threshold voltage, may not be constant in the device, right? VTH may change. It depends on the external and process parameters. For example, temperature. This is an external factor. If temperature fluctuates, so can VTH. Why does it happen? Suppose we have a band diagram like this. This is a NMOS. Sorry. This is N-type material. Okay. So this is a Fermi level. Fermi level, this is a hypothetical level which states that at zero temperature, 0 Kelvin, the states below it are occupied and above are empty. So when temperature changes, and this is a temperature dependent level because this doping, the concentration of dopants here, Nd positive, depends on the temperature. That means the electrons coming here, the number of electrons coming here and from these locations. Similarly, from the EV. It depends on temperature. And we know that a device is completely turned on when we are talking in context of a MOSFET. Let's say this was a PMOS at first. So when we have abundance of electrons in the conduction band, and let's just use the abundance here word because there is a clear definition for the threshold voltage. So when we achieve that concentration, my device turns on, and it solely depends on the and that potential, that is threshold voltage, depends on the positioning of this Fermi level. Okay, but this Fermi level is dependent on this position depends on the temperature. So when temperature changes, your EF energy, there's a reference energy changes as well. So what does it do? It changes the change the voltage at which device turns on. So it may affect the threshold voltage. It is like this. Let's say I had a PMOS when it's completely on. Sorry. Here EF is above EI and here it comes close to EC. So we have a abundance of electrons in conduction band. Initially, it would have been like this, assuming that there are no oxide charges. This is called as bulk potential, fire. So when we change the temperature, delta T change the concentration of Na negative in PMOS, sorry, NMOS, because we are dealing with P-type substrate, and Nd positive in Nd positive will be NMOS, right? No, NMOS not. It would be PMOS. Na negative in NMOS, Na positive in PMOS. Also, it depends on oxide thickness. That is, the threshold voltage will depend on the oxide thickness. We have a MOSFET. This is my oxide. A channel is formed here. This is main drain, this is main source. So, threshold voltage, the voltage after which the device turns on, will depend on the thickness of this oxide. And it may change as well. We have one of the effects that's called as Pauli depletion effect. Or we have another one, we have quantum mechanical effects. Also, that we already discussed, that is doping. It may change. So there are factors which can change the threshold voltage. So now, if I use expression for of GM as KW by L VGS minus VTH, and I say that in VTH I have a change. Let's say this is VTH dash. This is initial VTH plus delta times VTH. This is my change. Now my GM dash, let me say the GM naught was without any change. It was VGS minus VTH. Okay. So this will be KW by L okay, it will be delta VTH. So the GM dash will be, what is this? This is my GM naught, right? GM naught minus KW by L delta VTH. If I write here like this, and from first, if I divide both sides by VGS minus VTH, VGS minus VTH, I get and what is this KW by L VGS minus VTH? It's GM naught, right? Therefore, GM dash minus GM naught is delta GM by GM naught is equivalent to delta VTH by VGS minus VTH. Similarly, this is a change in my GM if there is a change in delta VTH. So we have this, right? So let's call it equation number 3. Now, there may be change in mobilities as well, right? The temperature can dictate the scattering events in the device, right? Which may in turn change the mobility. Let's say my mu dash, mobility dash, is mu naught plus delta mu. This means my k, which is equal to mu naught, let's say this was my initial, let's say this is k naught, mu naught cx, right? So now my gm dash will be mu dash c ox w by l vgs minus vth. I'm writing vth because now I'm I'm trying to get the expression for uh, GM dash or delta GM when only there is a change in mobility. So we'll see, substitute the values for mu dash, that is, substitute the expression. Okay, so my GM dash will be mu naught C of W by L VGS minus VTH plus delta mu C of W by L VGS minus VTH. So this is my expression. First one, let's say this gives my GM naught. This is my GM naught. Okay, and this is delta mu. So what is this expression? This is if I say from GM dash expression, which is mu dash C of W by L VGS minus VTH. So can I write this expression as GM dash by mu dash is equivalent to C of W by L VGS minus VTH. So I can write a delta mu dash by mu dash GM dash, right? One second. So this will be delta GM Okay, let me just write here not GM dash. Let's say this is my initial GM, that is when there is no change. So I can write here mu naught. Okay, yes, that is correct. So this is my GM naught. So here, this is not GM dash. This will be my mu naught, GM naught. So this will be my delta GM, that is GM minus GM naught, and I will transpose this to the denominator on the left hand side, and this will be delta mu by mu naught. So this is my expression number 4. So there is a change in mobility. So the device is sensitive to the mobility change. Now, using current source, we have equation number 2, Gm as square root of 2k W by L times I. I is my current source. From equation 2, Gm is 2k W by L times I. My I is here the current source. Now if VTH dash is VTH plus delta VTH, that is, there is a change in the threshold voltage. Since I is fixed, because this is my source current, GM dash after change in threshold voltage will still be 2 kW by L times I, because this current is fixed, no change. Therefore, GM dash delta GM or not GM dash delta GM is 0. Okay, so that is one advantage. The device is not sensitive to change in threshold voltage. Now mobility change. Now GM naught is 2 mu naught C ox W by L I, and my GM dash is 2 mu plus delta mu, mu naught plus delta mu, C ox W by L times I. So I can write it as 2 mu naught C ox W by L times I 1 plus delta mu by mu naught. Okay, let me repeat it here. GM dash 2 mu naught C ox W I by L is GM naught. So it will be square root of GM naught. Sorry, no. Square root of 2 mu naught C ox W by L I will be GM naught, and I have 1 plus delta mu by mu naught raised for omega. Now from binomial term and using this expression 1 plus delta mu, where delta mu by mu naught is less than 1, I can use the approximation of the first order. So my GM dash will be GM naught 1 plus delta mu by 2 mu naught 1 by, sorry, not 1 by 2. That comes in the moment. So this will be GM naught, GM dash minus GM naught by GM naught is equivalent to delta. Implies delta GM from this expression, we see that sensitivity drops by drops to half of the previous value. Okay, so from the previous expression, we had that delta GM by GM naught is delta mu by mu naught, and now we have by 2 mu naught, and we don't see any change in delta GM due to change in threshold voltage, and the change in mobility brings a half of its value. on the previous. So, okay, now let's have a little bit of introduction. The current mirror. From the topic, what do we infer? Current mirror. So it mirrors. So in terms of MOSFETs, one MOSFET will mirror the current of the another MOSFET. That is the current flowing through the another MOSFET will be mirrored. Okay. So if I have two MOSFETs, let's say. If I have MOSFET like this, for example, M1, and M2, if somehow I can configure this such that the current flowing through this transistor MOSFET is I1 and this is I2. We will say this is a current mirror if I2 is equivalent to I1. Okay? So how do we do that? We have this is an NMOS. What is done is connect your drain terminal to your gate and you connect these two gates and you attach a current source here. So let's say this is IS. So what happens is initially M1 is off, right? So you need a potential at gate. Let me write it. We need a, let's say this is G1, this is my G2, this is T2, S2, and this is my T1, this is my S1. We need a gate to source voltage, that is VGS1, to turn the device on, to turn on the device. Right? So what happens is initially at first IS is greater than I1. I1 is technically 0 at first, right? So I1 is technically 0 at first. So what happens is, for this transistor, we have a often in transistors we do have parasitic capacitances, right? So this is IS and this is my I1. So what will happen? Let's say this is ICP. My IS will be equivalent to ICP plus I1. When I1 is 0, the whole current flows through the capacitor. So you may get confused here that how does the current flow through the capacitor? So you should understand that the capacitor is not charged at first, right? So unless it gets fully charged to a potential same as the source potential, it can draw the current. This is basically charging. It charges at the one terminal. Let's say this is coming here. It gets charged here and it charges here the other plate and which can draw the electrons on the another side. Let's say these are the positive charges coming here. That way, capacitor can conduct initially. Once it's fully charged to a potential such that it equals its source potential, it can block the voltage. So what happens here is the potential VCP starts to increase. So what does that do? It increases the gate voltage, that is VG, because VCP, let's say this is my VCP. VCP is connected to gate, so it increases VG. And what does that do? It increases I1, right? So when I1 increases, this is a continuous process, right? This process stops when IS becomes equivalent to I1, and it will give us a particular gate voltage. So when I1 keeps on increasing, your ICP starts decreasing. Okay, and that means you will reach a stage when ICP will be 0, but it will remain at a particular potential, and your VCP will be equivalent to your gate voltage. That will dictate now your other transistor, other transistor. Okay. So now, if I have a configuration like this, assuming 1 milliampere of current, source current, assuming 1 milliampere of current coming here, and assuming a condition when I1 is equivalent to IS. So it may be given by kW by L VGS minus VTH whole square. Okay. So if it is 1 milliampere, assuming kW by L as 1 milli, so this is assuming VTH as 1, so I can write VGS minus 1 is plus minus 1 volt. So what will be the correct answer? For NMOS, it should be 2 volt. So I get a potential of 2 volt here, which will be also applied to my M2. So for M2, I will get a current of I2. Since for the current mirror, the transistors should be identical, so it will be 1 milli times 2 minus 1 whole square, that is 1 milliampere. So this is how the current mirror works. Okay, so I hope that was clear about the current mirror. So let's now solve few of the problems. The circuit here shown consists of 4 transistors, and it's given that all the 4 transistors are identical. The values of device parameters for all 4 transistors are given. kW by L is 1 milliampere, VTH is 1, and channel modulation parameter is 0.01. The supply voltage is 12 volt and reference current is 2 milliampere. I refer to the circuit shown in this figure. Find the DC voltage V3. We need to find V3 between the drain of M3 and ground. Okay, so this voltage. Such that the DC current flowing through M2 or M3 is exactly 2 mirrors. That means it mirrors the left portion. So what we will do is, we will calculate V2 as well as the gate voltage and then also V3. Okay. My reference is 2 milliampere. So first we will calculate gate source voltage of transistor M4. Let's use a MOSFET expression. Slide it here. IM4 will be equivalent to kW by 2L VSG. Sorry, this is not VSG. This is NMOS, so this should be VGS minus VTH whole square. So for the current mirror, the current flowing through this transistor should be 2 milliampere, and in any case it should be 2 milliampere at a steady state because the elements in series should have the same current, right? Because this is an infinite resistance, so zero current here. So this is 2 milliampere. kW by L is 1 milli by 2 milli 2. So this is VGS minus 1 whole square. Milli and milli will cancel. So this is 4 is equivalent to VGS minus 1 whole square. So this is basically VGS 1 plus minus 2. So the answer should be 3 volt. This is VGS 4. So VGS 4 is 3 volt. Since same current flows through M1, this implies VGS 1 is also 3 volt. This implies VG1 is 3 volt since VS1 is grounded, that is zero potential. So what does that signify? VGS4, which will be equivalent to VG4 minus VS4, and VS4 is VG1. And it's 3 volt. So this implies VG4 is VG1 plus 3, that is 3 plus 3 volt, is 6 volt. So VG4 is 6 volt. Okay. So this is how we calculate the potentials. So I got VG1 as 3 volt, VG4 is 6 volt, but we need to calculate V3. Also, let's calculate V2. Since this is the current mirror, so VGS across M4 should be same as VGS across M3. So this implies VGS 3, which should be equivalent to VG3 minus V2, it should be equal to 3 volt, and VG3 is VG3 is equivalent to VG4 is equivalent to 6 volt. Therefore, V2 will be 3 volt. So V2 will be 3 volt. And also for transistors, all the four transistors to have same current flowing, drain potentials should also be same. So what does that mean? The drain potential across transistor M3 is V3. So my V3 should be equivalent to the drain potential across F4, that is VG4, which is 6 volt, right? Or it is VGS M4 plus VGS M1, which is 3 plus 3. So you, what do we study in this course? What do we learn? We learn how to calculate multiple potentials in a current mirror. Okay. Now the next question is find the small signal output resistance looking into the drain terminal of M3. to draw an equivalent circuit with gate biases for M4, M1, it will be M4, M1, it will be zero gate bias. So see here, we need to find the resistance looking into this terminal. So we will attach a source here, IX, VX. VDD will be grounded, so that means, and IRF is open, so it will have infinite resistance, so it will have also zero potential at gate. That means no current is flowing. So that means gate potential of M1 is also zero. So that means M2 gate potential is also zero. Okay. Now we can draw the. That makes M3 gate potential only gate VG is zero. Let's see. So let's start from. Let's start from the MOSFET M3. We have GM3, VGS3, and its resistance. We have to find this resistance. So we have this potential here. Okay. Attached is the transistor M2. Okay. And we have R01, GMV, GS1, and we have R04. Gate voltage is zero. This gate voltage is also zero. So let's call it a potential V2. Since gate voltage is zero here, one second. So this is my GMVGS2, which is equivalent to VGS1. So we have a gate potential of zero, so no current is flowing through this terminal. No current flowing through here, no current flowing through here. So it is the zero potential, this is the zero potential. So there will be no effect of R04, right? So let's see. Writing a KCL at output node, KCL. So we have Ix is equivalent to Vx minus V2 by R03 plus GMVGS3. Okay. So Ix is Vx by R03 minus V2 by R03. Look here, for VGS3, VG is 0, but there is V2. So this will be GM times V2. Right? So I have Ix is equivalent to Vx by R03 minus, let me just repeat it first, V2 by R03 minus GM V2. So what is V2 though here? V2 is, current will be Ix, V2 is Ix times R02. Therefore Ix will be equivalent to Vx by R03 minus Ix R02 1 by R03 plus GM R02. If I take the same variables on the same side, I'm taking Ix as common, so this will be 1 plus R02 by R03. Wait a second. So this is only GM here. This will be GM R02 and this is Vx by R03. So my Vx by Ix, which is my R out, will be R03 plus R02 common 1 plus GM times R03. So this is the resistance value. Now I have this. What I need to find is R03, R02 and GM. We can find that, right? We have very information given in the question. R03, since the transistors are identical, will be equivalent to R02, will be equivalent to 1 by lambda ID. And since we are using the same circuit, the current in the IV transistor is 2 milliampere and lambda is 0.01. So it will be 0.01 times 2 milli. It is equivalent to 50 kilo ohm. And what is GM? GM is 2 times I kW by L, which is 2 times 2 milli, and kW by L is 1 milli, and it comes out to be 2 millisiemens. So I have every value. I can calculate now. R out, which is R03, that is 50 kilo ohm, plus R02, which is again 50 kilo ohm, 1 plus GM times, that is 2 milli, R03, that is 50 kilo ohm, kilo and milli we can see. So if you calculate it, it comes out to be 50 kilo ohm plus 50k multiplied by 101, and it turns out to be 5.1. Okay. So refer to the circuit, again same figure, find the minimum value of V3 with which the small signal output resistance remains high. Okay, so here, small signal output resistance remaining high means device remains in saturation. From the characteristics, we know that this is a low resistance region, this is a high resistance region. So the question is to find the value such that the output resistance remains high. So indirectly, it says that the device should remain in the saturation. So what should be the condition? The drain source voltage M3 and M2, because all the device need to be in saturation, should be such that the devices remain in saturation. Right? So if I have this is 93, okay. So V minimum, besides that, it should be VDS of saturation of 1 second. This is M3. Sorry. VM3 saturation and VM2 saturation. That will give me my minimum voltage. So VM3 saturation is, it should have a voltage of VGS3 minus VTH. Similarly for this voltage as well, it should have VGS2 minus VTH. Since VGS is same, so this will be one second. If it is at a minimum voltage, we are talking only about V3 minimum. Right? That is okay. This is not a minimum case. So my V2 should be at its highest value, right? If it is at its highest value, so even for that case, my V3 minimum should be such that V3 minus V2 is still above VGS3 minus VTH. So this is V2, which is 3, and VGS3, this is 3 minus 1 plus 3. So V minimum, which is a terminal 3, drain terminal of transistor 3, should be equivalent to 3 minus 1 is 2, 2 plus 3 is 5 volt. Because if we treat V2 saturation as well, that can go a slightly lower value, and that would have given me the answer of 3 minus 1, that is 2 plus 2, 4 volt. But if now V min, V2 is at 3 volt and V minimum is 5 volt, 5 minus 4 is 5 minus 3 is 2. Wait a second. 5, 4 minus 3 is 1 volt. So the device will not remain in saturation, because for the saturation minimum voltage should be 2 volt. Another way that is simpler, V3 minus V2 should be saturation voltage. So that is simply VGS3 minus VTH, because this should keep your transistor in saturation. So this is V3 minus V2. This is VG3 minus V2 minus VTH. This is cancel. So V3 is VG3, that is 6 minus 1, 5 volt. Okay, we have two more questions. The circuit shown in figure, okay, these are the values. Let's just jump to the final question. What is the question? Refer to the figure this. Find the ratio of R1 by 2, R1 by R2. Find the ratio of R1 by R2 is equal to R3. So that the nominal current ISD is 2 milliamp. So the current flowing is 2 milliampere. We need to find R1 by R2 is equivalent to R. So R1 by R2 is equivalent to R3 by R4. Okay. So we have ISD1 is equivalent to KW by 2L. VSG, since this is a P and PMOS, VSG1 minus mod of VTHP whole square. So this is used as a current source. ISD1 is 2 milli. KWL1 is 1 milli by 2. This is VSG1. VSG1 minus VTHP whole square. This is mod, right? So this is 2 to 4. This is 4, okay? And this is square root. So this will be VGS1 minus VTHP. So this is basically VSG1. I always write it VGS1. VSG1 will be how much? 1 plus minus 2. So VSG should be positive. So this is VS. VS is my VDD. And VDD, sorry. This is VTHP. VTHP is, okay, VTHP is 1.5 volt. And VDD is 10 volt. So VS here is 10 minus VG1 is equal to 8.5 volt. So my VG1 is 6.5. So now my VG1 is 6.5 volt, which is this potential to ground. Here, this is ground. So which will be given by a voltage divider. Okay. So this VG will be equivalent to R1 by R2. R1 by, sorry, not R1 by R2. This will be given by R2 divided by R1 plus R2 times VDT. So this is 6.5. R1 plus R2 is equivalent to R2 times 10. So 6.5 R1 is equivalent to 10 times R2 minus 6.5 times R2. So 3.5 R2 is equivalent to 6.5 times R1. So what I need to find is R1 by R2, R1 by R2, and which is also equal to R3 by R4, because this is the same voltage divider we need to consider here to get a gate potential similar to this potential. Is equivalent to R1 by R2 is equivalent to 3.5 by 6.5, and it turns out to be okay, so simple. So now last, okay, we have two questions. Find the precise value of DC output voltage V out. Okay, this is the VR voltage. We need to find this. Mhm. So we have a drain potential here, we have a drain potential here. So these two voltages should be equal. So drain potentials should be equal. Therefore, VD3A, that is the drain potential of transistor 3A, is equivalent to V out. And VD3A is the gate potential, which should be VGS3A. VD3A is equal to VGS3A. And since the same current flows through every transistor, that is equivalent to 2 milliampere, IDS is kW by 12 VGS3A minus VTH whole square. IDS, that is 2 milli, is equivalent to kW by L is for NMOS is 0.25 milli by 2. This is VGS3A minus 1.5 uh, 1.58 whole square. So this turns out to be VGS3A is equivalent to 4 plus 1.5. This is 16. Square root of 16 is 2. We take the positive value. So VGS3A is 6.5 volt. So that means VD3A is 6.5 volt and my V out is 6.5. No, sorry, 5.5 volt. Okay, now last question. Find the small signal voltage gain in the mid frequency range. That means the input capacitance will be shorted. We may need again to draw the equivalent circuit. So let me quickly draw it. So we need to find V output by V input. V input is given to the M1 transistor. So VDD is 0. M2 and M3 will not figure in this case. So I have equivalent circuit like this. So we have same drawing first the transistor GMVSG R not 1. This is grounded and V out is here. R not 3B. This is GM VGS3B. This is my V out. Now if you look at the figure, this gate voltage is 0. 1 second. This gate voltage is 0. This gate voltage is 0. So my GM3B is 0. GM3B is 0. So nothing goes here. ACL add V output. So we have V output by R naught 3B is equal to current coming in. That is GM So I'm using GM because every transistor will have a same this should be 1, same GM, plus 0 minus V output by R not 1. So here this is V output by R not 3V is equivalent to GM. What is Vs here? 0. And what is G? In. So this is minus V in. And this is minus V out by R1. So taking the V out on the left hand side and taking common, so this is 1 by R naught 3Z plus 1 by R naught 1 is equivalent to minus GM V in. So my V output by V in is minus GM R naught 3B parallel R naught. And I need to calculate R naught 1, it should be equal to R naught 3B is equal to 1 by lambda IT, and it is equivalent to 1 by 0.01, that is your lambda, and ID is 2 milli. This comes out to be 50 kilo ohm again. And GM, do the calculations, it turns out to be 2 millisiemens. Therefore, gain, which is V output by magnitude of V output by V input, that is gain is GM times R naught AB parallel R naught 1, it comes out to be 50. You can substitute the values and get the answer. So here you can see that gain turned out to be due to the parallel resistance R naught 3B and R naught 1. So if we directly look here, so this is indeed a parallel combination of R naught 3B, R naught 1. With so this is your finalized. So, so I hope the session was nice. You watched the whole video. If any case you have any questions, you can always post in the form or in the YouTube. Thank you. I guess that's it for today. Let's meet in the next session.